Hey, stats kids. Today we're looking at section 5.4, sampling distributions. Buckle in because this is going to be a fun one on stats with Mr. Forbes. Notes out, and away we go. All right, so we're starting sampling distributions. And this one just has a lot to it. So this may be a little bit longer video, so you may have to finish this one up at night or something if you're at school, or just get you a bowl of popcorn if you're at home or something, and we'll knock this one out. So here we go. We're looking at a sampling distribution. This is different. It's very similar to what we've been doing, but it's very different. And we're still going to be looking at the probability distribution of a sample statistic. Here's the biggest difference. Everything we've done so far has been pick one person, pick one thing, pick one person, one event. Now we're switching. So now instead of picking one person, we're picking a group. So in the problem, when it says they pick 30 people, they pick 60 people, they pick 100 people, that switches from what we've been doing with normal distribution to a sampling distribution. This is formed when samples of size n are repeatedly taken from a population. So now we're looking at more than one. So everything we're doing today, when you look at the problems in the homework, it's going to be more than one person. So we're picking 30 people, we're picking 50 people. That's going to be a sampling distribution, not just a normal distribution. That's going to change a little bit of the math. And on the test, it's going to change some of the stuff you're going to have to do math-wise, so pay close attention to that. The first thing we're going to do then is see what that sampling distribution actually means. And so if we take any population with a mean and a standard deviation, we're going to take all these different samples. So there's like a gazillion people, and we want to say, what's your favorite soda? So we're going to take a sample of one group, we're going to take a sample of another group, we're going to take a sample of the third group, and that was probably a bad example because we want a number. So we're going to take a sample of, how many rolls of toilet paper you use in a month. That'd be a funny one. And so we're going to take all these different samples of how many rolls of toilet paper people use in a month. And we're going to get all of these different averages, all these different means, because we're going to get a bunch of different groups. Now, they should be similar, but there are going to be some differences. And we're going to come up with this idea. The mean of the sample mean, so if we do a sample distribution and we do all the samples, the sample mean is equal to the population mean. We're going to make that assumption that the mean of the sample distribution is equal to the population mean. Here's the biggest difference. When we're taking more than one person, we're taking a group, we have to change our standard deviation. So the standard deviation of the sample means, sigma of the sample, is equal to the population standard deviation sigma divided by the square root of the sample size n. So now every time before we run normal cumulative distribution on our calculator, or every time we find the z-score, we have to change sigma by dividing by the square root of n. That's called the standard error of the mean. And we're going to do that when there is more than one. Now, the first thing we're going to look at is actually proving, or not proving, but at least I'm going to show you that that is true, that the mean of the samples is equal to the population mean, and that the sigma, the standard error of the mean, is sigma over square root of n. And we're going to look at two examples. We're going to find the mean, variance, and standard deviation. So the population values of 1, 3, 5, 7 are written on slips of paper and put in a box. 2 slips of paper are randomly selected with replacement. Find the mean, variance, and standard deviation of the population. Find the mean, variance, and standard deviation of the sample means, and compare our results. So here is part A. We'll call this A, B, and C. Let's find the mean, variance, and standard deviation of the population. Well, we can do that really easy by using our calculator. And I just put my calculator away, so let me get my calculator back out. To do that, we're going to run one variable stats. We're going to put that in our calculator. So stat, edit, and we want, let me clear this one out. So we want 1, 3, 5, and 7. And we want quit, so stat, and we want to run calc one variable stats. We'll do that in list 1, calculate. So we get for 1, 3, 5, and 7. Then we get a mean that is 4. And we get a sigma that is 2.23. 2.236. We'll call that. So there's our, and that's for the population. That's our population. Now, B, we want to look at the mean, variance, and standard deviation of the sample means. All right, how are we going to do that? Well, we are picking two slips of paper are coming out of the box. So we're going to look at all of the possible combinations. So we could pick a 1 and a 1. We could pick a 1 and a 3, a 1 and a 5, and a 1 and a 7. We could pick a 3 and a 1, a 3 and a 3, a 3 and a 5, and a 3 and a 7. And hopefully you see what I'm doing here. I'm just looking at all the different combinations that could occur. Could get a 5 and a 1, a 5 and a 3, a 5 and a 5, and a 5 and a 7. And I could get a 7 and a 1, 7 and a 3, 7 and a 5, and a 7 and a 7. So those are all of the possibilities. And I want to find all of their means. So I'm going to add and divide by 2. I'm going to do that in a different color. So add divide by 2, that's 2 divided by 2 is 1. 4 divided by 2 is 2. 6 divided by 2 is 3. 7 divided by 2 is 4. We get 2, 3, 4, and 5. We get 3. There's a nice little pattern that forms. 4, 5, and 6. And we get 4, 5, 6, and 7. So there's all of our sample means. I averaged all of the possibilities. And now with all of those numbers, I want to find the sample mean. So I want to find the mean of my samples. And I want to find my standard deviation of my sample means. And to do that again, I'm going to use list. So stat edit. And I'm going to put all of the red numbers now in my list. So 1, 2, 3, 4. 2, 3, 4, 5. 3, 4, 5, 6, and 4, 5, 6, and 7. And we want to see what happens when we run our one of our stats on it. And we get a mean that is, look, the same, 4, and I just gave it away. What do you notice about the mean of our samples and the mean of our population? They are the same. And that was our note from our last lesson. So the mean of the sample mean is equal to the population mean. So that approximates it. Next, what do we get? We got a sample standard deviation of X. And for that, our sigma was 1.58. Now, where did that 1.58 came from? Because we didn't get that with the population. We got 2.236. Well, remember, we have a formula. We're going to take our 2.236 and divide it by the square root of n. And here the square root of n is 2. That was how many we picked at a time. So if we do 2.236 divided by the square root of 2, what do we get? I didn't get my decimal in there. 2.236 divided by square root of 2. What do we get? Looky there. We get the exact same thing. So that verifies our formula that the standard deviation of the sample is sigma over square root of n. N is how many we are picking. Part C then, we just compared the results. We saw then the mean of the population is equal to the mean of the sample. And we saw that the standard deviation of the sample is equal to sigma over square root of n. So we just proved those are true. Try yourself one as you go through that again with 1, 3, and 5, and we'll run through that again. So if we look at a sample size or sample space of 1, 3, and 5, we're going to put those into a list, and we'll run one variable stats on it. In fact, I would encourage you to pause the video and try to work through this yourself. and see if you can come up with the same answers. When we find the average of these, we get a mean of 3 and a sigma of 1.633. And now we're going to go through and we're going to pick 2 at a time out of just 1, 3, and 5. That's going to give us a 1 and a 3, a 1 and a 5. I forgot a 1 and a 1. It's going to give us a 3 and a 1, a 3 and a 3, a 3 and a 5, a 5 and a 1, 5 and a 3, and a 5 and a 5. And we're going to take the average of these. That's going to give us a 1, a 2, a 3, a 2, a 3, a 4, and a 3, a 4, and a 5. And we're going to run our 1 var stats on that in a list as well. And we're going to see what we get. So the mean of the samples, when you run this, you're going to find out that you're going to get the exact same thing as the mean of the population. And then sigma of the sample is going to be sigma over square root of n. That's our 1.633 divided by square root. We pick 2 at a time, and then we'll get that on our calculator. And when you look on your calculator, when you run this on 1 variable stats, you're going to get 1.15, the same thing. So again, we're verifying that the mean of the sample is equal to the population, and the standard deviation of the sample is equal to the population standard deviation divided by square root of n. Okay, so that verifies what we said had to be true. The next part is we're going to introduce a new big idea in statistics. And that big idea is this central limit theorem. Now, up to this point, we've only worked with sets of data that are normally distributed. Well, it turns out the world is a really messy place. Not all data, in fact, most of data is not normally distributed. So we can't really use normal distribution with it. But it so happens there's this thing called the central limit theorem. And it says as long as we take a sample size of n greater than or equal to 30, so as long as we're picking 30 people or more, or 30 things or more, then that population will approximate a normal distribution. Yep. So here we take a distribution that is not normally distributed. It's not a nice bell-shaped curve. As long as we are taking more than 30, then we can use normal distribution. And that's pretty much the important thing. So when we're looking at the example problems, one of the things we'll talk about is n greater than or equal to 30? That's our big idea on this one. Or is the data normally distributed? If neither one of those work, we can't do the problem. It's just, we're done. You can't do it. So n has to be bigger than 30 or has to be normally distributed. So let's flesh that out. In either case, the sampling distribution of the sample mean has a mean equal to the population mean. We've already verified that. And we found our sigma for our sample mean is our population standard deviation divided by square root of n. So we've already verified that. And again, this just reinforced the idea. We can take an ugly distribution, one that's not normally distributed, as long as n is greater than or equal to 30. Then when we start picking stuff, we're going to approximate a normal distribution. So now we get into some examples. So here are cellular phone bills for residents of a city. Have a mean of $63 and a standard deviation of 11. So let's identify that stuff. Well, let's pause for a second. Let's go through the rest of the problem. Random samples of 100 cell phone bills are drawn from this population, and the mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution, then sketch a graph of the sampling distribution sample space. So what do we know? First question is, can we approximate this distribution with normal distribution? And we're going to look to see how big are we picking. So n is 100, and that's bigger than 30. So yes, we can use a normal distribution. The next part is find the mean and standard error. Well, the mean of the sample approximates the population mean. They give us the population mean. That's going to be $63. Then we want to find the standard error of the mean. That's sigma over square root of n. That is, there's the standard deviation of 11 divided by how many are we picking? We're picking at 100. So 11 divided by the square root of 10, and that's $1.10. Last part then, sketch a graph. Well, that's going to be a normal distribution. Our mean we know is in the middle. That's our $63. So the first standard deviation is going to occur at $1.10 up from 63. So that's 64.10. And then our -1 standard deviation will be minus $1.10, which would be 61.90. So there's our graph of the distribution. Go ahead and pause the video and try it yourself too on your own, and then play the video and see how you did. All right, the first thing we need to look at is can this be normally distributed? Yes, we can, because n is 64. Therefore, everything applies. The mean then of the sample approximates the mean of the population, and that is the same. We're doing the same problem, so that's still 63. However, our sigma changes. That's going to be 11 divided by, because n changed, is the square root of 64. And so now we're looking at 1.375 as our standard error of the mean. So now we have a curve. Our middle is still the mean. The mean is 63. But what happened to our standard deviation? Well, we picked less people. So when we look at our standard deviation and we add $1.37 to this, we get 64, about 38, I rounded up, I think, and 62, and we subtract. What happened to our standard deviation? Well, it got wider. I didn't spell wider correct. It got wider. Why did it get more wide? Well, we have less people, right? And the first one we had 100. Now we're down to 64. So we have less people. So our information is less accurate. So to keep the same amount of information, we have to have a wider standard deviation to get the same amount of information. So that's what's going on in that problem. Example 3. The trending heart rates of all 20-year-old athletes are normally distributed with a mean of 135 beats per minute, a standard deviation of 18 beats per minute. A random sample of size 4 are drawn from this population. The mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution, then sketch a graph of the sampling distribution sample. Well, your first thought is, well, n is 4. And Mr. Forbes, you've just been saying for the last 15 minutes, that's got to be bigger than 30. It does, unless it's normally distributed. So there is our magic key phrase. It doesn't matter that n is under 30 as long as we are normally distributed. So now we get to keep on going. So our sample mean is approximated by the population mean, which is 135 beats per minute. Our sampling error is sigma over square root of n. Sigma was 18 divided by the square root of 4, and that is 9. So let's sketch a graph. So our graph is our normal distribution. The middle is 135 beats per second. We're going to add 9 and subtract 9. 135 plus 9 would be 144. Subtract 9 is 126. So that would be our graph. Try yourself 3. Again, go ahead and pause the video and try that one on your own, and then see how you did. Diameter fully grown white oak trees are normally distributed with a sample mean of 3.5 feet and standard deviation of 0.2 feet. Random samples of size 16 are drawn. Is n bigger than 30? It is not. Doesn't matter because the diameters of fully grown white oak trees are normally distributed. So that was our second condition that allows us to keep working with the problem. Our mean then is the population mean, which is 3.5 feet. Our standard error of the mean is our sigma, which is 0.2 divided by the square root of 16. We're going to put that on our calculator. That is 0.05. Therefore, we want to sketch a graph. Our graph will be our normal curve. The mean goes in the middle. That's our 3.5. Our first deviation and our second deviation, we're going to add 0.05, not 0.5, but 0.05. That gets us 3.55, right? Think of this as 3.50. Subtract 5 gets us to 3.45. All right, next part is now we want to find a z-score. To transform x bar into a z-score, we're going to do the same thing, x bar minus the mean over standard deviation. But now because we're picking a group, that sigma changes into our standard error of the mean. We have sigma divided by square root of n. Other than that, all of this problem is the same as what we did in 5.2, 5.1 and 5.2. We're gonna put this back into normal cumulative distribution function. But we have to get our z-score first. Now this one, you cannot type into your calculator by putting in the mean and sigma because the sigma changes. So on these, we do have to find the z-score. You can't just type all these into your calculator like I showed you on the 5.2 video. So here we go. First, can we use normal distribution? We can because n is bigger than 30. That's our central limit theorem. Therefore, our mean is going to approximate the population. And that is 25 minutes. So 15 to 19, that's 25 minutes. And our sigma, we have to change this one, is 1.5 divided by square root of n. And we picked 50 drivers, so that's divided by square root of 50. And therefore, well, we're going to take care of that in the problem, I guess. I missed that part. We want the x value. We're going to have two x values. We have a 2.47 and a 25.5. So we're going to set x equals to 24.7 and x equals to 25.5. Now we're going to go back to the same formula we used in 5.2. And we're going to say our z, and I'm going to call this the z left score, is our x bar minus mu. So that's our average goes first. 25.5 minus 24.7 divided by sigma. Our sigma was 1.5 divided by square root of 50. And I really recommend you put that bottom in parentheses and even put that top in parentheses too to make sure you don't make a calculator error. And when you type that into your calculator, you're going to get a negative 1.41. Remember, your z-score should be somewhere between -3 and +3. If not, there's a good chance you made a mistake. Go back and put in more parentheses. Our z right-hand score then is our bigger number, 25.5 minus 25, and I did something wrong. This was supposed to be a 25. I used the wrong number, sorry. That's still the correct answer because I'm looking off my notes, but no, that's the correct, I used the wrong number. 20 minus 25, that's the mean, that's the correct number, divided by 1.5 divided by square root of 50. Again, put parentheses on all that. That'll get you your right-hand z-score of 2.36. Okay. So there is we're back to standard normal distribution because we got z-scores. So our mean of 0 is in the middle. We have a negative 1.41 to the left and a 2.36 way over here to the right. So we want to find the area between. So we're back to normal cumulative distribution function from negative 1.41 to 2.36 for 0 and 1. And we'll type that into your calculator. And that should give you a 0.9116. So what's the probability that the mean time a person aged between 24.7 and 25.5 spends driving to work? There's a 91% chance. There's our probability. And we're feeling like we're doing actual statistics. Good feeling. All right, try it yourself too. Go ahead and pause the video and see if you can get that one on your own. Do all the same steps we did for the example 4 and try it yourself 4. All right, here we go. First, can we use normal distribution? We can, because n is 100, which is greater than 30. So that matches our central limit theorem. We're looking at drivers from age 15 to 19. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5? We're using mean still of 25 and standard deviation of 1.5. So given a mean of 25, we want P of X to be between 24.7 and 25.5. And we're going to find our z-score. So for an x score of 24.7, we're going to find our z left score. That's going to be our x bar minus mu over our standard error of the mean. And that is, we want the average to go first. I lied. We want the number to go first. I put x bar, that should just be x. So 24.7 minus 25, that's our average is second, divided by our sigma, which is 1.5, divided by square root of 100. And again, I recommend putting the top in parentheses and the bottom in parentheses so you don't make a calculator error. And that gets us something really close to negative 2.0. And then we have an x score that is 25.5. So now we want a z-score to the right, which is x minus mu over sigma over square root of n. And that is now 25.5 minus 25 over sigma, which is our 1.5 divided by square root of 100. Put those in parentheses. On your calculator, you should get 3.3. So if we look at a picture of that, we're back to standard normal distribution. So our mean is 0. We're way left at negative 2. We're even further right at 3.33. Well, that's like almost everything under the graph. So this will probably be in the 90s, probably in the high 90s. And so we're going to do normal cumulative distribution function from negative 2.00 to 3.37 with a mean of 0 and a standard deviation of 1. We'll type that into our calculator and you should get 0.9768. So there's a 97, almost 98% chance that when you do a sample of 100 drivers, their average times will be between 24.7 and 25.5. That's how that works. Other things we do. So we did between. There's other directions we can go. So now we look at a less than. The mean room and board expense per year at a four-year college is $9,126. You randomly select 9 four-year colleges. What is the probability that the mean room and board is less than $9,400? Assume the room and board expense is normally distributed with a standard deviation of $1,500. First question, can we even do the problem? N is not bigger than 30. Does that mean we're done? No. Because why? They are normally distributed. So there's our magic 2 words. We're normally distributed. So we can find our mean. The average cost of room and board is $9,126. And we want what? We want the probability that X is less than 9,400. It always helps to set up this probability statement because that will help you with your graph, knowing which way you need to go. So we need one z-score. And again, that's x minus mu over sigma divided by the square root of n. We're going to plug in the sample, our sample average. And that was 9,400 minus the average, 9,126, all over our sigma, which is 1,500, divided by square root of n. Again, put parentheses on all that. That should give you a z-score of 0.548. Now let's look at our graph. Again, our graph will help us figure out what to type into our calculator. We're back to standard deviation, standard normal distribution, excuse me. 0.58 is somewhere to the right of 0. And we want everything that is less than. So we're going to the left. So we're going to do normal cumulative distribution function to the left bound. Well, that's negative infinity. So we're going to call that negative e to the 99. Stopping at 0.548, 0 and 1. And we're going to type that into our calculator. That's going to give us a percentage, 0.7082. So we're going to pick 9 four-year colleges, and we will see what's the probability that their room and board is under $9,400. Well, there's a 71% chance that their room and board is under $9,100. Again, pause the video, see if you can get this one on your own, and then play the video and see how you do. Here we go. The average sales price for a single family house in the US is $176,800. You randomly select 12 single family houses. What's the probability that the mean sales price is more than 160,000? Assume sale price is normally distributed with standard deviation of $50,000. First, can you do the problem? Right, n is 12. Well, that doesn't work for central limit theorem, but they are normally distributed. So we can keep on going with the problem. That gives us a mean, population mean, 176,800. And then we want what? We want the probability that X is greater than, so we're looking at greater than $160,000. We need to find our Z-score. Because we're picking more than one, we have to use a sampling distribution. That is X bar minus mu over sigma square root of n. That is 160,000. Missed a zero there. Minus our 176,800 population average divided by sigma, which was 50,000, divided by square root of 12. Again, put parentheses on that. And when you type that into calculator, I got a negative 1.16. All right, so let's look at our normal curve, standard normal curve. Mean is 0. Negative 1.16, well, that's left of the point of inflection, so negative 1.16. We want the area where? Well, we want X to be greater than our Z-score of negative 1.16. So we're going to the right. So now we're looking at normal cumulative distribution function. Our left bound is negative 1.16. Our right bound is e to the 99. 0 and 1 is our mean and standard deviation. When we plug that into your calculator, you should get a 0.8770. So if we pick 12 single family houses, the probability that their mean sale price is more than $160,000 is 87, almost 88% likely to happen. That's how we interpret that. All right, next up. An education finance corporation claims that the average credit card debt carried by undergraduates are normally distributed with a mean of $3,173 and a standard deviation of $1,120. Can we do the problem? Well, it tells us that they are normally distributed. So yes, we can do the problem. Part A, or the first part, what's the probability that a randomly selected undergraduate who has a credit card holder has a credit card balance less than $2,700? Are we picking a person or are we picking a group? When it says A, we are picking one. So we're picking one person here. That means we're back to what we did in lesson 5.2. So our Z-score is just X minus the mean over sigma. Really, it's divided by square root of 1, but we know that that's just the same thing. So that's just our Z-score. That is 2,700 minus 3,173 divided by 1120 is our standard deviation. And that gets us a Z-score of negative 0.4223. And what do we want? We want the probability that is less than. So we want the probability that X is less than $2,700. Therefore, when we look at our graph, our left-hand bound is negative infinity, so normal cumulative distribution function, negative e to the 99. We're stopping at negative 4.223, 0 and 1. That gets us a probability of 0.3364. That was for one person. Now we're going to take the same parameter, but now we're going to select 25 people. So now we've switched from a regular normal distribution to a sampling distribution because we're picking more than one person. First off, can we do the problem? We can because we know it's normally distributed. So now we have to change our Z-score because we're doing a sampling distribution. X bar minus mu over sigma divided by the square root of n. So that's 2,700 minus 3,173 divided by 1120. But now because it's a sampling distribution, we have to divide by square root of 25. Don't forget your parentheses there. And that gets you a Z-score. And I didn't write that one down, so I need to do this on my calculator. So again, parenthesis, 2,700 minus 3173, divide by parenthesis, 1120, divided by square root of 25. Whoops, that is not right. Divided by square root of 25. That gets me a z-score of negative 2.11. And so we're going to do normal cumulative distribution function. We want less than, so we have negative infinity, so negative e to the 99. We're stopping at negative 2.11, 0, and 1. We're going to punch that into our calculator. Second distribution, normal cumulative distribution function, that works. We're at negative 2.11, paste, and we get a really small number, 0.017. Now, here's the question. Why did we drop so much? Why did we drop from a 33% to a 0.017%? Well, here's the idea. Because we went from one person, we don't have a very good idea of what's going on. But once we get 25 people, we get a lot more information to deal with. So we can get a better probability. If you look, 2,700, that's pretty far underneath our average of 3,173, right? That's a pretty big difference. So if we pick one person, there's only a 33% chance that they have that low of a credit card balance. But if we pick 25 people, that's a lot more that have to be under that average. And it's going to be very, very rare to pick 25 people, have all of them be under average of whatever thing we're talking about. So this goes really small. Again, why? Because we have more information. So the more people we have, the more information we have for our problem. I'm going to let you try yourself 6 on your own, i.e. I'm going to skip that one. So we talked about finding sampling distributions and verifying their properties. We talked about the central limit theorem. N has to be bigger than 30 or essentially distributed. And then we applied that to our problems. Your homework for 5-4 then is page 269, problems 2 through 42 evens. We're going to do 11 instead of 14 because I had you pick 3. This one only has you pick 2, so we're going to do 11 instead of 14. Have a good day, Maroons.